So the first functional imaging technique here I want to talk about is something called PET scanning, which stands for positron emission tomography. And basically, this involves radio-labeled materials being injected into your bloodstream and carried to your brain. And these radio-labeled materials will decay. And when they decay, they emit typically a positron, which is a subatomic particle, which is the antimatter equivalent of an electron. And this is not in a physics class. You have to go to physics to learn more about that. But when it encounters the electron, it apparently decays. There's sort of an explosive annihilation of the two, and gamma rays head off in different directions. This is electromagnetic radiation that you can't detect with your retina. We don't have photoreceptors that can detect gamma rays. However, we've developed machines, gamma ray detectors, that can sort of detect simultaneous arrival of gamma rays from either side and extrapolate back into the brain, where that particular annihilation event actually occurred. And so the power of PET is that you can radio label a lot. So one thing they often radio label for functional imaging studies is oxygen. So you can have O15, which is going to emit or release a positron, right? And it'll convert a proton, I believe, into a neutron, so you'll get a different atom. But basically, it's carried in the blood, and because it's carried in the blood, remember that neurons, when they are more active, right, they are going to, via the astrocyte detection of activity, coupled to the capillaries, right, there's going to be this expansion of blood flow into a region of the brain where there's more neural activity occurring. So there's a lot of very local control over blood delivery into different regions. So if an area of the brain is being utilized, well, more oxygenated blood is going to work its way into that region, and so you're going to get a bigger radioactive signal, gamma ray signal actually, coming from that area if it is being utilized during the performance, let's say, of some task, right? So PET takes advantage of the radioactive decay of chemicals that are injected into the bloodstream, and it can give you information about changes in blood flow into different regions that are associated with increases in neuronal activity. You can also, for example, radio label other compounds, actually, and see and get some functional information utilizing PET. So there was one study, for example, that looked at adolescents who were playing video games in a PET scanner, and they injected these adolescents with a radio-labeled compound that bound to dopamine receptors. And when dopamine was released, naturally released in, let's say, the nucleus accumbens, you would see displacement of that radio-labeled dopamine agonist, right? You would basically, what the chemical that they had ejected that was radio-labeled was bound to the receptor unless dopamine came out. If dopamine came out, it would be removed. It would be displaced by the actual dopamine, and it would be removed from the area. So they found they could get measures of dopamine activity, how much dopamine was being released when these adolescents were playing video games, and it turns out, obviously, there was quite a bit of dopamine being released when they were playing video games, actually, when, they were anticipating, somebody was going to come around and shoot them on a game or something along those lines. So PET has some great advantages in that you can radio label multiple different compounds, and so you can get a sense of activity in many areas of the brain. As a functional imaging technique, we'll see along with fMRI, it's often utilized to measure activation, which literally means areas of the brain that receive more blood flow, right, during the performance of particular tasks.